discussing linear algebra, and so far in our linear algebra part we have learned certain theory of linear algebra. We have seen linear equation solvers, both direct and iterative, and we have seen the linear equation solver can also be used in a system of nonlinear equation in conjunction with Newton-Raphson methods or similar method. Now we'll leave the linear solver now and we'll get into the second problem of linear algebra, that is the problem of finding eigenvalues and eigenvectors. And in particular, one method that what we will learn is something that we call power method. And let us see how to do it. Remember the very basic eigenvalue problem for a matrix A, which is a square matrix. Eigenvalue lambda is given by AV equals lambda V, where V is the eigenvector of the matrix and V cannot be a null vector. If it is null vector, then the problem becomes trivial. V is corresponding to the eigenvalue lambda is called the eigenvector of this matrix A. Now, the characteristic polynomial of matrix A, which is indicated as P lambda, is a function of lambda, which is determinant of A minus lambda I. So I is the unit matrix of same dimension. And setting this P lambda equals 0, we will get the eigenvalues. The root of P lambda equals 0 are the eigenvalues of A. Once we get the eigenvalues, we can use this equation AV equals lambda V and we can get the eigenvectors. This is how we actually get eigenvectors when we study analytically. So let us take an example to see and to remember what we did in our study of eigenvector in standard mathematics classes. Here we are interested about the dominant eigenvalue, and by dominant we means that eigenvalue which is bigger in absolute value, and the corresponding eigenvector corresponding in the sense which is coming from this dominant eigenvalue, that eigenvector of matrix A is 7, 3, 6, 4. So how we are going to get this eigenvalue and eigenvector? We have to get the eigenvector lambda by using this determinant A minus lambda I equals 0, which gives us this 7 minus lambda 3, 6, 4 minus lambda. This determinant is equal to 0. So if I take this determinant, this will be 7 minus lambda multiplied by 4 minus lambda here, minus 3 into 6 equals 0. So this is a simple quadratic equation. We can solve them and we get lambda 1 and lambda 2 at 10 and 1. These are the two eigenvalues. Therefore, the dominant eigenvalue obviously will be 10, that is the bigger eigenvalue. Okay, so now we want to get the corresponding eigenvector of A. So corresponding means the eigenvector that will come from this dominant eigenvalue lambda 1 equals 10. To get the eigenvector, we go back to this usual equation that AV equals lambda V. In this case, AV1 is our eigenvector corresponding to the eigenvalue lambda 1, which is 10 here. I can write it A minus lambda 1 V1 equals 0. So clearly V1 equals 0 is a solution of this equation, but we are not interested about that. Eigenvectors are actually non-zero vectors that we are looking into. This is an equation set of linear equation, but this is homogeneous set because right hand side is 0. We want to see that if there is any non-trivial solution for this V. That is the purpose here. So A minus lambda I V1, we can write this lambda 1 is 10. So 7 minus 10 and here 4 minus 10, v1 equals 0. So I have minus 3, 3 and 6, 6, v1 equals 0. Clearly v1 equals 0, we will not take that. We'll see any other value. So here minus 3 plus 3 equals 0, 6 and minus 6 equals 0. Therefore, the v1 is 1, 1. With this will be satisfied. Of course, you can say that, well, why 1, 1? I can take 2, 2 or 3, 3, 5, 5, anything will satisfy. So the problem is that eigenvector is not something unique. Scalar multiples of v will also be eigenvectors in this case. So usually when we write eigenvectors, you can write any of these vectors, 1, 1 or 2, 2 or 3, 3, it doesn't matter. But usually what we do is that we normalize v. By normalize v means that we divide v by the norm of v. And norm of v in this case is root over 1 square plus 1 square, so root over 2. So if we divide v by root over 2, then I get the normalized eigenvector, and that is usually how we represent eigenvectors. So this hat sign is indicating the normalized vector. So this normalized vector is v1 divided by norm of v1, and norm of v1 is equal to this root over 1 plus 1, 1 square plus 1 square, so root 2, which means this will be 1 by root 2, and v is 1, 1. So this gives us 0.707, 0.707 as our eigenvector. So now we have solved the problem. Our dominant eigenvalue is 10, and our dominant eigenvector is this 1, 1 or its multiple. So we are writing it in a normalized manner, that 0.7071, 0.7071. That is our dominant eigenvector normalized. The absolute value or the norm of this vector is obviously, it should be 1 because this is already normalized. Norm of a normalized vector is 1, of course. All right. So this is the way we find eigenvalues and eigenvector analytically. These are the exact values, but now we have to see that how can you get these values numerically. Numerically, what we will use is something we call power iteration or power method. So power method is applicable for, of course, a square, that is, let us say n by n. All eigenvalue problems are related to square matrix. So I have an n by n diagonalizable matrix. Now diagonalizable is something that theory we are not discussing here, but I believe that in your maths course you might have learned what is diagonalizable matrix. But without going into any great detail, I will only mention that diagonalizable means this matrix must have linearly independent eigenvectors. Such matrices, actually you can use a similarity transformation and you can transform them into a diagonal matrix, but that is not important for us now. Only to know that power iteration is possible for diagonalizable matrix. Okay, so what do we do in such a matrix? In such a matrix, let us say the eigenvalues are lambda 1, lambda 2 up to lambda n number of eigenvalues, and the corresponding eigenvectors are v1, v2, etc. up to vn. What this method does is that it will give us the v1 and lambda 1, where this lambda 1, its absolute value is greater than the absolute value of any other eigenvalues. In other sense, this is the dominant eigenvalue. So power iteration will give us the dominant eigenvalue and its corresponding eigenvector. So that is the key about power iteration. We need diagonalizable matrix and we get only the dominant eigenvalue and its corresponding eigenvector. How do we get it? Well, it's very simple. The idea of power iteration is that we start from an initial guess of this dominant eigenvector or eigenvector corresponding to the dominant eigenvalue, and then we iterate till convergence. How? That is, the V in k minus 1th iteration will be A matrix multiplied by v of kth iteration. We start from a guess of v0, then I calculate v1, which is equal to a multiplied by v0. Then I calculate v2, which will be equal to a multiplied by v1, etc., etc. So it's a very simple technique. Now you may be wondering that why this will actually give me the correct eigenvalue and eigenvector, and that is a interesting question, and we will answer this question. We'll look into this question later on. But right now, let us see that if it at all works. It will work, we know, but it works or not, we have to check it out. Okay, so this is the key of vk plus 1 is a vk. That is the algorithm. Now let us say that I go with this and I iterate till convergence and I get some v, acceptable v, and I say that, well, this is my v, my eigenvector. Once I get the eigenvector, I have to get the eigenvalue. So it is other way around. In analytical solution, we first get the eigenvalue and then we calculate the eigenvector. Here we get the eigenvector first and then we calculate the eigenvalue. How do I get it? I come to this AV equals lambda v, and then I take an inner product. AV dot v is equal to lambda v dot v. So AV dot v is a scalar and v dot v is also a scalar. AV is a vector just like v, same dimension, so their dot product will be a scalar. So this is actually, this AV is like this. So first I'll do an AV and then I'll have a dot product will v. So my lambda will be AV dot v divided by v dot v. So that gives us the eigenvalue. All right. So now I know that how to get the eigenvalue or eigenvector. But then for the sake of convergence and for the sake of keeping the error small, we play some trick. So if I keep on multiplying a with v continuously, then it's very difficult to know that it is really converging or not. That is what we do is that we normalize after every iteration. So when we normalize this vk plus 1, I'll normalize with this v hat I'll take. So this is normalized. So vk plus 1 is this avk divided by the norm of avk. Of course, in kth iteration also we have normalized. So that is why this kth iteration also I have written an hat sign here. So every iteration this is normalized, kth iteration v hat, and then as I come to k plus 1th iteration, av divided by norm of av, that gives me vk plus 1. Once I get this vk plus 1, I can calculate this lambda, which will be k plus 1th lambda based on this vk plus 1. So a vk plus 1, you can see that av dot v divided by v dot v. So av dot v is a vk plus 1 dot vk plus 1, and because this v's, all these v's are now v hat, they are all normalized vectors, so their dot product v dot v should be equal to 1. So there is nothing there. Here this is v dot v is simply 1. Therefore this is our algorithm for power method. I start from some initial guess v0. It's actually good to start from a normalized vector, but even if you don't start with a normalized vector, it will still work. And then I take this first step, I calculate this v1 normalized from this v0, I get lambda 1 then, and this is how it will go on until convergence. Now it is easier to see the convergence because v will look similar as I go from one iteration to another. Lambda will obviously look similar as I go. Okay, so let us see an example that how it works. So consider this matrix A once again 7 3 6 4. We are already familiar with this matrix. We did an analytical solution over this matrix. Now what we will do, we will use the dominant eigenvalue and the corresponding eigenvector using power method. We understand the algorithm as this: avk divided by avk, norm of avk, and the lambda will be given by this. So now to use power method, we will start from a reasonable assumption, but before that we remember the exact solution is lambda equals 10 is the eigenvalue, and eigenvector normalized is 0.7071, 0.7071. So we start from our assumption of V naught is the initial guess, 0th iteration is 1 0. 1 0 is a good guess because it is normalized, one of them is 0, so it is, when you have 0 it is easier to do this multiplication, it's less work. That is why you take this kind of a guess. There is no other reason for this. Otherwise this guess is random. All right, so what would be my V1? So my V1 will be from here AV0 divided by norm of AV0. I can calculate this. I have A7364, V0 is 1 0. So calculation of this is simple. 1 0, if I multiply here, then I'll get this V1 is with the multiplication of 1 and 0, this will be 7 and 6. So this 7 6 divided by this norm of 7 6. So if I take this as hat, then 7 6 divided by norm of 7 6. This is how we will continue, and what we will get is this 0.7592, 0.6508. This is my V1. Now I can calculate this lambda 1. Lambda 1 will be a scalar, that is AV1 dot V1, and if I do this calculation, I know the V1 now, I know the A now, so I'll get this value of AV1 dot V1 will give me 10.17647, etc. Similarly, I can get this V2, that will be AV1 divided by norm of AV1. In a similar manner, I do the calculation and I get 0.7124, 0.7018. Lambda 2 is coming down as 10.02205. We keep on doing this, and let us say up to V3. Then I have AV2 divided by norm of AV2, it is coming 0.7076, 0.7066. Lambda 3 is AV3, V3, it is coming 10.00225. Clearly you can see that the solution definitely is going toward the exact solution, that is lambda 10 and V is 7071, 7071. This is the exact solution. You can see that lambda started from 10.17, then 10.02, and then 10.00 we have reached. And here also V, you see that 7565, 7170, now I have 7070. So we are reaching toward exact solution. So at some reasonable point, we can now stop iteration. One way of thinking about it is that we can have a convergence criteria that when we see that our lambda is not going any further, we have sort of close enough. So between two iteration, if I see the change is very small, I can stop there. That would be one way of doing this. There are many other ways of defining the convergence criteria. That would be one way of doing it. Okay. All right. So now see, let's move ahead, and here we see the Python program. This is the program. This is a typical Python program for power method, and this is the program I wrote and ran just to show you the result that I was showing in previous slide. Here you can see that this is the initial guess of our eigenvector, and this is the matrix A, that is 7364, and this eigenvalue 100 and error 100, these are just arbitrary number to start the iteration because this is a while loop, so I need some value of this error to begin with. So I have arbitrarily just given some value, error equals 0, and this error is the difference in absolute value between these eigenvalues, new and old. So I have given some arbitrary eigenvalue. So what I am doing is that as long as this error is greater than this max error, I am taking this A dot V. So remember that here this is the algorithm, that V is AV divided by normalized AV. So this is a np.matmul is a matrix multiplication between A and V. So this is the AV, and I am normalizing this AV. So this is normalized AV. To normalize, I am using this function that is normalizing it. This is a function that normalizes a vector x by doing x divided by norm of x, and norm I am calculating using the inbuilt numpy routine, that is numpy lineal.norm. So now the V is normalized. So this V is already this Vk plus 1. We get it in one line. Then my eigenvalue is, this will be my eigenvalue. So eigenvalue is the inner product of this matmul AV, the A and V, it's product of A and V with V, whatever the inner product, that is my new eigenvalue. Then I calculate the error, and then the eigenvalue, I put it there, this new eigenvalue. That is how we keep on doing it, and this iteration goes on until we hit a reasonable value, where I have here given this eigenvalue minus eigenvalue. It will hit less than 10 raised to minus 8, which seems reasonable in this case. This is not for very high accuracy calculation. This is just to see us that if this method works. So this is a reasonable convergence criteria. And if I run this, it will take a fraction of a second, and it will give us the output of 10.0000, etc. So many zeros. So you understand that we are sort of doing all right here. And the V, that is the eigenvector, that is giving us 0.707106787, 707106778. You remember this was the exact solution. Exact solution was 10 and 0.70717071. So clearly our output is good enough for our conceptual learning, and we are pretty sure that we are in right track. So this is how the power method works, and you can play around with this code. You can run it and see that how it works. Okay, now in summary, we have seen that this is a very simple tool, and it just requires matrix vector multiplication and nothing else to find the dominant eigenvalue and the corresponding eigenvector for diagonalizable matrix. Of course, it's very difficult to know beforehand a complex matrix that will be diagonalizable or not, but that is a different discussion. We don't want to bring it up here. For your exercise, you take this matrix 7 3 6 4 once again. First, you analytically find the dominant eigenvalue of A inverse, and then numerically try to find the dominant eigenvalue of A inverse. And we'll talk about it more in next lecture, that how to do it numerically, but you can find it out because you know power method. Some version of that will use it later on to find the eigenvalue of A inverse. So that's all for this lecture. Thank you, and I'll see you in next class.